So I posted the newest lesson, which is also the last lesson, which is on Newtonian gravity. And you probably haven't had a chance to look at it, and that's fine. And it's about Newtonian gravity and also about orbits. So there's a pretty decent example in the lesson about orbit. It involves the space shuttle, I believe. Yes, or the International Space Station. So I thought I'd do a different example today, comparing the Newtonian gravity to the plain traditional gravity that we use. And here is a quick overview. The force of gravity is equal to, with a capital G, is capital G, capital M, little m, over r squared. And the capital G is a number. It's on the equation sheet. It's 6.67 times 10 to the minus 11th. There are units, but they're a pain. Newton meter squared per kilogram squared. Notice the kilograms squared are canceled by the kilograms in the two masses, and the meters squared in the numerator are canceled out by the two factors of meters in the denominator. So the units of the overall thing come out in newtons, like they're supposed to. Capital M is the mass of the planet or the moon or the sun. So I'll look up the mass of Earth here. And the mass of Earth is 5.97 times 10 to the 24th kilograms. Earth. And one of the important things about Newtonian gravity is that the distance value we use is not as flexible as what we're used to. So we're used to the idea of being able to set y equals 0 wherever we want, and we can't do that with Newtonian gravity. We have to measure r as a center to center distance. And note that our Earth is 6371 kilometers. So let's try a calculation, and we'll do it by both methods and see. Oh, one more thing about Newtonian gravity. The potential energy of Newtonian gravity is minus g m over r. So we don't get to use the simple mgy formula that we use for regular gravity. So I want to do a comparison of our plane gravity that we use on Earth and Newtonian gravity. I need to get my little calculation window going here. So let's see here. So let's launch a projectile straight up at 1,000 meters per second. And we'll ignore the spin of the Earth. The spin of the Earth would make this weird. And we're going to ignore air resistance. yeah, that's the way I want to phrase it. So we'll compare our F equals mg to Newtonian gravity. So let's first look at the initial acceleration. So if we use the force of lowercase g equals mg, that is ma, then we should make it negative because it's downwards. And that will make a equals minus g, which is minus 9.8 meters per second squared. In Newtonian gravity, maybe I should make regular gravity a different color because I had Newtonian gravity being red up there. Yeah, there we go. So in Newtonian gravity, we would have minus force of capital G equals minus g m over r squared is ma. So a would be minus capital G capital M over r squared. And I need to fill in some numbers now. Minus 6.67 times 10 to the minus 11th. Mass of Earth, 5.97 times 10 to the 24th. And then divide by 6371 kilometers, so times 10 to the third. Kilograms stay, but kilometers need to be converted to regular meters, and the denominator is squared. So capital G, 6.67 e minus 11, capital M, 5.97 e 24th, and our Earth is 6371 E3, and A is that times that over that squared, and it comes out to 9.81 meters per second squared. So far so good. The two methods are producing the same result for the acceleration immediately after launch. So let's calculate max height. So using regular gravity, we'll use PE of regular gravity is mgy, and set y initial equals 0. We'll assume y equals 0 is the bottom. So then we get to do 1/2 mv squared equals mgh. It's nice and easy because our initial potential energy is 0 and our final kinetic energy is 0. And then the little m's cancel, and we can plug in the 1/2 times 1000 squared equals 9.8 h, and find out that h is h is 0.5 times the 1000 squared, and then we have to divide by 9.8, and we get 51,020. 51,020 meters is our max height. Now, when we do it by Newtonian gravity, PE of Newtonian gravity, as I mentioned, is minus capital G, capital M, M over R, not squared for potential energy. It is squared for the force. R is squared for the force, but not squared for the potential energy. And R initial is equal to 6371 times 10 to the third. We don't get to set R equals 0 at the beginning because R equals 0 is when the center to center distance equals 0, and we're not starting from the center of Earth, we're starting from the surface of Earth. So then we have to set up minus G M M over R initial plus 1/2 mv squared equals minus G M M over R final plus 0 at the end. Now notice we can still cancel out the little m's. That would be the mass of our object, the mass of our projectile. So let's calculate that thing. So this is minus 6.67 times 10 to the minus 11th and 5.97 times 10 to the 24th all over 6371 times 10 to the third, not squared. So PE initial over M is minus G times capital M time divide by the radius. Fix my formula before I give you my result is, and I want to get an extra digit of precision here. So this is minus 6.520 times 10 to the 7th. And it would be units of energy if the little m was still in here. So now it's units of energy divided by mass, or joules per kilogram. So let's figure out that part over there. So that's 1/2 times 1,000 squared is 1,000 squared is a million. Half of that is 5 times 10 to the 5th. Yes. So now let's take note of where we are. So the whole equation is going down there. This is minus 6.520 times 10 to the 7th plus 5 times 10 to the 5th equals minus GM over R final. Well, to me, I think it would be a good idea to turn these things into regular numbers. So let's combine these. So this is 0.5 times 1,000 squared is 500,000, and that plus that is minus 6 point, oh, I'm dyslexic. This is 2.5. Sorry. I did the calculations and I switched two numbers in my head. So I'll fix that in the notes. But for now, I want to leave it there corrected in case you're writing things down. so that you know the correction I made. So then this becomes 6.200 times 10 to the 7th is minus G capital M over R final. So then we multiply both sides by R final, which cancels it out over here. And then we find out that R final is, the minus signs also cancel. So we get 6.67 times 10 to the minus 11th times 5.97 times 10 to the 24th. That's capital M. We have to divide both sides by 6.2 times 10 to the 7th. And we get our final is 6.67 times 10 to the 11th times 5.97 times 10 to the 24th divided by energy final 6.42. Let me increase that a little bit. Yeah. So 6.422 times 10 to the 6th. That is 6422 kilometers. Now remember, our initial was 6371 kilometers. Our final is, let me write it above so I can subtract. Our final is 6422 kilometers. So height by this method is, that's a 1, 12 minus 7 is 5, and we get almost the same result. I need more digits of accuracy in order to see the difference between these two methods. So let me get more accuracy out of our final is 6422.378 kilometers. Our initial was 6371 kilometers. So that means H is 51.378 kilometers. And before, using the original method, we had 51.020 kilometers. So we see that the answers are different by about 1%, or about one. They're different by about 358 meters out of 51,000 meters. Which is a little bit under 1% error. But if we launched even higher, this problem would get even worse. So apparently I should have done a 2,000 or a 4,000 meter per second launch in order to really see the difference between these two methods. Let me do one more calculation with this. Let's find the acceleration at the top of the trajectory by both methods. So using lowercase g, we just have a equals minus g equals minus 9.8 meters per second squared. Using Newtonian gravity, capital G, A, oops, A equals minus gm over r squared. So we have minus capital G, capital M over r squared is minus 6.67 times 10 to the negative 11th, 5.97 times 10 to the 24th, divided by 6.422 times 10 to the 6th squared. So this is minus g times mass of Earth divided by the radius squared. Minus 9.65 meters per second squared. So at 51 kilometers altitude, the force of gravity is actually a little bit smaller than it would be at the surface of Earth, and hence the acceleration due to gravity is a little bit smaller than at the surface of the Earth. So that's kind of an interesting thing about doing calculations in Newtonian gravity as opposed to doing calculations in plain gravity at the surface of Earth. Now, in the notes, I went over the circular motion and orbits and how all of that looks. So please go ahead and review the notes that I posted under remote lecture materials and possibly watch the video lesson. And then you should know what I'd like you to know about Newtonian gravity.